Hello class. This is going to be the last video for the last homework. On page 12, 12.1, 12.2, 12.3. And this is another one on cross sections, which is good because cross sections are weird and I definitely want to make sure you guys understand it. So looking here, the first question is asking you to identify the two-dimensional cross section of the following solid. We're doing a cone first. So again, I brought up that website that I was using a lot in class. I can move our little slices up and down. We can see the different shapes of our cross section. I can tilt the plane that's cutting us, which is really important because we definitely need to understand the difference between a slice that is at an angle with the base. That's what we're seeing now. We're slicing diagonally through the cone versus when we slice parallel to the base. And so, the first question is saying, what do you get when you are parallel to the base? And so here it is. You can see this much more clearly if I show you a little more of the website. So let me bump this out. So over here you can actually see that circular cross section. And you can see as I slice closer to the base, we get a circular cross section that's pretty big. It's almost as big as the base itself. As I slice up nearer to the apex or the vertex of this cone, we get a much smaller circle. But no matter where I slice, I'm always getting a perfect circle, right? And so we talked about how, in the last homework, that when you slice parallel to the base, you're always getting a cross-section that is similar to the base. Remember, similar means exact same shape, just a different size. So we're getting a circle. And that's it. We could fill that in now. So we know that as long as we slice parallel to the base, we get the same shape as the base, which is a circle. Now it says, what about a cross section that's perpendicular to the base and does go through the apex? By the way, the apex, I don't think I've ever said the word apex. I almost always call it the vertex. But that, of course, is that point right there. So, if I were to take this, and if I start tilting my slicing plane, does that look perpendicular to you? That's close. I wouldn't say it's quite perpendicular. Let me keep tilting this a smidge. Whoa, 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 whoa. I guess that is perpendicular. So that's meant to be perpendicular right there. So if I spin this around, you can see that if I do not pass through the apex point, then we get this shape here that you might remember from Algebra 1 is called a parabola. That's not an ellipse anymore, right? An ellipse would eventually close up. It would come around and be more of an oval, but this thing is always getting wider, wider, wider as you look up and down. So that's not an ellipse, that's called a parabola. And, well, that's not what we wanted anyway. So if I actually move my slice to where it does intersect the apex, again, if I'm over here, that's not hitting the apex. But then right there, we hit the apex. And you can see now that my sides are no longer curved. They're perfectly straight. And as I run across the base, I'm perfectly straight. So my cross section now is a triangle. So keeping it kind of simple, when I use a slice perpendicular to the base, but I do pass right through that apex, I just get a triangle, which I think is kind of easy to picture, hopefully. But again, if I move that slice closer to the edge, then suddenly as I pass through the rounded side of the cone, we get a rounded cross section, and suddenly we're getting a parabola instead of a triangle. So hopefully that helps you understand that question. So again, our answer here is, it's just a triangle. Now, I don't think you are asked to draw this, but I think it's probably a good idea to draw it anyway. So I would do that. I'm going to do it. Whether you guys do it or not, it's up to you. But let me make a couple copies of this. So again, if I'm doing a cross section, oops, you guys can't see that. I'll put one here, whatever. But if I do a cross section that's parallel to the base, then you can imagine a plane slicing straight across like this, and your cross section would go bzz, bzz, and we get that circular cross section. That is not the best drawing ever, but that's okay. Next, if I used a slice that was perpendicular to this cone, like that, then maybe you can tell that if I pass right through here, we come straight down that face, straight across the center of the circle, straight down the rear face, and instead of any curves anywhere, we do get a nice straight triangle. But again, there you go. That's how you need to be visualizing this stuff in your head. Okay. Oh, it's dark in here. There we go. So number 2 is a rectangular pyramid. So the base isn't a square anymore. It's a rectangle. I don't know if I can do that here. So I can change this to a pyramid all of a sudden. This pyramid has a base that is a pentagon. I definitely don't want that. So I can change it to 4 sides. But I think it's always going to be a square. I don't think I can mess with this to where the base is going to be an actual rectangle. So that's okay. We can use our imagination, hopefully. So the first question again is, what if you're parallel to the base? So we change our angle, and right there I'd say I'm parallel. And as I slide up, as I slide down, you guys see that we're always getting a square. And more generally, what we're really getting is a shape that is similar to the base, right? So that means if we're talking about this actual rectangular based cone, then a slice that's parallel to the base is going to give us a cross section that is not a square but a rectangle. It's going to be similar to our rectangular base, so it's going to be a rectangle. Hopefully that makes sense. Now it says, how about a cross section that's perpendicular to the base but it does not pass through the apex? Alright, so for that, I think you want to look at this thing again. So I'll tilt my intersecting plane until it's perpendicular. That's perpendicular right there, I would say. So if I make sure that I'm not passing through the apex, if I'm here, then we can see we get, in one instance, we get an intersection that's a quadrilateral. It's got 4 sides, but none of them are parallel, none of them are congruent. It's just a quadrilateral. Now, if I tilt my plane just right, then I can get a trapezoid. I can't quite get it. But maybe you can use your brain and just sort of imagine, if this base is parallel to this base up here, then we are going to get a perfect trapezoid that time. So I can twist this around. Maybe you can see that's a good trapezoid. But the one last intersection that's possible, and this intersection is always going to be possible, is I can twist my intersecting plane. I can move it way out to a corner. And we can see that it's certainly possible to get an intersection that's a triangle. So the best answer to part B of this problem is that really there's sort of 3 different kinds of intersections. We might get just sort of a plain old quadrilateral. We might get a trapezoid. Or if we pull our intersecting plane way out to a corner like this, then we just get a triangle. And that'll do it. And then finally, what if our cross section perpendicular to the base has to go through the apex? Well, if I have to go through the apex, then as I pull this thing in to where it touches the apex, then we see we're definitely getting a triangle. And no matter how I spin this, it's a triangle. So that's it. The only possibility when you go through the apex is a triangle. And so you could draw that if you wanted to. You could imagine coming down this front face. You could imagine going down that rear face and then running across the base here. But you're just getting a triangle. So there you go. There's that one. Number 3 is a hexagonal pyramid. So I think I can do that here. We just, if you look here, I can go from a triangular base to a square base, to a pentagonal base, to a hexagonal base. So here it is. If you look straight down at it, you can definitely see that we're dealing with a base that is a hexagon, or if you look at it from underneath, there's your hexagon. So I don't know, maybe let's jump right to part C. Part C says a cross-section perpendicular to the base and through the apex. From before, it still works. We can see again that anytime we're perpendicular to the base and passing through the apex, we're still getting a cross-section that's just a triangle. So there's no way around that. They're trying to show you that that's true of every pyramid no matter what the base is. So if my base is a hexagon, I still get a triangle. If my base was a square, I still get a triangle. So for part C, you can definitely just call it a triangle. And if you want to try to sketch that, then maybe let's imagine coming down this face here. We hit the base here, then come down this face back there, hit the base there, and then we run across the bottom of the base, and we see we're just getting a triangular cross-section out of it. I hope that cross-sections parallel to the base are pretty easy by now. If I'm parallel to the base, then I get the same shape as the base. So since this pyramid's base is a hexagon, you should be expecting to see a cross-section that's a hexagon, just smaller. And lastly, a cross-section perpendicular to the base but does not go through the apex. This is that kind of tricky one again. I could slice here near a corner and I could get a triangular cross-section. I could slice a little more carefully, maybe over here. So I'm going to pass through this triangle. I'm going to go down this triangle. I'm going to go down that triangle, and then I'm going to go across the hexagonal base. And that guy there is going to be a perfect trapezoid. But we also saw on the website that there is a way to do a cross-section where, how do I do it now? I don't know. I think we just kind of do it at an angle. So if I slice through here on an angle so that I hit this point low, but I hit this point high, then I can run down this face and I can run down, what, this face or something, and then run across the base. And I can get a four-sided figure where the sides are not parallel. It's just a quadrilateral. But it's not a special quadrilateral. It's not a trapezoid. It just has four sides. But those are your options there. So moving on, we're on the second page now. It says state the cross-section if a plane intersects the cone as shown. And so as shown here, I would say that this is not parallel to the base. This seems to be at an angle to the base. And so you know that's going to be an ellipse. We've seen that a bunch of times, so I'm not going to make a big deal out of it. You should know by now that if you intersect a cone at an angle, instead of a circle, you get a circle that's been a little bit stretched in this direction. So there's a long dimension and a short dimension. That's not a circle, that's an ellipse. So for 5, it says the square pyramid is cut along the shaded plane shown below. So which of the following is the cross-section of this solid? That's kind of hard to visualize. I'll try to show you on the website. I want a square-based pyramid. And what are we doing? I'm trying to be at an angle, maybe like that. But we're over there closer to the edge. Maybe parallel, kind of like that. That looks like the right slice to me. Doesn't that look right to you? But I would say that is definitely the slice that's giving us our trapezoidal cross-section. Right, just like that. So that to me seems like it's option B. Let me get rid of this extra junk. Then we can see our choices a little better. It's not A. We're definitely not going to get a square. B seems right to me. It's definitely not C because we don't intersect only 3 faces. We definitely intersect 4 faces. We're intersecting 3 triangles and the square bottom. So I'm expecting 4 sides. And D is not right either. It's definitely B. So pick option B. Alright, what about 6? 6 says that a square pyramid is cut along the shaded plane shown below. Which of the following is the cross-section of the solid? Well, if this is a square pyramid, and this cross section definitely looks parallel to me, then you should be expecting a cross section that is a square. So this is F. It's not G. We're not going to get a rectangle because we're going to get a shape that is similar to our base. So it's going to be a square. Triangle, I mean, no, don't be silly. Trapezoid, definitely not. It's got to be a square. 7 says, what is the least number of sides for a cross section of a pentagonal pyramid? So okay, again, I'll show you that. So this is what a pentagonal pyramid looks like. You need a base that is a pentagon. Can I just turn this thing off? I don't think I can. Let's make it parallel. There's parallel, I guess. So just kind of get that out of our way. So what is the least number of sides for a cross section? I think we did this in the last homework, but maybe y'all didn't watch that video. But basically, the least number can always be found by just kind of going at a pretty extreme angle, come over here, move it to here. You can see that we can take just sort of a tiny slice over here at a corner. And if I take sort of the smallest possible slice I can, just over here at this one lonely little vertex, then we can slice off a triangle. And there's nothing less than a triangle, right? The polygon that has the least number of sides is 3. So since I sliced here and I got 3, that must be the least possible number of sides. So it's safe to say here that the least number of sides is 3. Now the greatest number of sides is a more interesting question, because we said the greatest number of sides is always going to be equal to the number of faces. And you can always figure out the number of faces that your solid has, especially with a pyramid. You know that a pyramid has only one base, and then it has a bunch of lateral faces, and all of those lateral faces are triangles. So if you think about it, our pentagonal pyramid is one pentagonal base, and then there's a triangle attached to here, and a triangle attached to here, and a triangle attached there, and a triangle attached there, and a triangle attached there. And maybe you can picture folding all of those triangles up, and they would meet at the top and give you your pyramid. But so that means I've got one base and I've got 5 triangular lateral faces. That seems to give me a grand total of 6 faces. So that means here that the greatest number of sides is 6, meaning the basically the most complicated cross section we could get would be a hexagon. And if anybody's interested in actually seeing what that looks like, then I'll show you. So first of all, I didn't know I could do this, but we don't have to be red all the time. Let's try green for a second. And then let me tilt this thing and play with it until I'm intersecting every single face. I wish this didn't go off the screen, but okay. So I gotta tilt, tilt, tilt. And definitely move the slice up. I guess right there I'm doing it. So here in this orientation, you can see I'm hitting the bottom, I'm hitting the base, I'm hitting this triangular lateral face, this triangle, this triangle, this triangle, this triangle. I'm hitting all the faces, and so I am getting a cross section that has 1, 2, 3, 4, 5, 6 sides. So there's my hexagonal cross section. You can see that it's definitely possible. I don't know if this helps anybody. Let me try to say it anyway. Imagine if this cone was like made of glass, and I could actually fill it up with green water, like green Kool-Aid or something. Can you imagine that there's a way I could hold this so that the surface of the water is nice and level? I could hold this cup in such a way that the water sits like this, and you can see that it would hit all 6 of the walls, right? I could flip this cone upside down. If I did it like this, how would the water fall? Well, the water would fall to the bottom, right? Now, can I do this? Maybe this doesn't work upside down. I'm not sure. I don't think it does. But, yeah, it doesn't work. It doesn't work like that. But okay, so imagine if I held it like this. If I held this nice and flat, then the water level would be nice and flat, and it would be parallel to the base, and I'd only touch these 5 walls, so of course my cross section would be that pentagon. But that's maybe an interesting thing to try to do in your brain, is just think of this as water. And as I move the cup around, the water sloshes around with it until it's level. And I don't know. I don't know if that's helpful. Maybe it's not. But anyway, there's the answer to 7. Let's move on. All right. So instead, well, maybe this is number 8. Maybe this is all number 8. And number 8 has like 9 parts. You've got, actually, maybe it's 12. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, 10, 11, 12, 13, 14, 15. All right, so there's a bunch of these questions. I'll try to go through them fast, okay? But it says here, for each figure and given plane, sketch and name the cross-section described. So the first question is as easy as it gets. We know that with a sphere, you just literally can't get any shape other than a circle. So if I'm supposed to have a slice that passes through the center, then even if I'm on a diagonal, I still get a cross-section that is a perfect circle. It couldn't ever be an ellipse. Now here in a cone, if I'm parallel to the base, we said that if you're parallel to the base, you'll be similar to the base, which means we're getting another circle. Here with a cylinder, if I'm parallel to the base, this time, instead of being similar to the base like I was in a cone, I'm congruent to the base. It's literally the exact same shape as the base, which is still a circle. So 1, 2, 3, done. Here I want to be parallel to the base. Well, it's a pyramid, so I'll get the same base, but I'll be similar to it. I'll be shrunk down a little. So I'm getting a square, but it's slightly smaller than the square. This says parallel to the base. Now, the base is not this rectangular bottom. Again, for the love of God, try to remember, base does not mean bottom. The base of a prism is one of the two faces that are the same and parallel. So if this pentagon here is my base, then I need to be parallel to that base. Okay? So again, this base, we could slide this thing back and forth. You can see that no matter where I slice, we're going to get the same shape as a pentagon. And here, I don't know if this helps, but I'll say it anyway. Maybe picture like a loaf of bread, right? If I was going to slice this up like a loaf of bread, slice, 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 then every slice of bread is going to have that same pentagonal shape, right? Anyway, I'll shut up. All of these are pentagons. And then here it says, we pass through the top with a horizontal plane. Passing through the top with a horizontal plane. All right, maybe this is kind of a trick question. I think they're talking about a plane that just barely touches the North Pole up here. So you might not think of this as a cross-section, but it counts as a cross-section. Our intersection would literally be just that one point. So our cross-section is a single point right at the very North Pole of our little globe. So that's kind of a tricky one. We haven't seen that before. 7. Let's be perpendicular to the base and pass through the vertex. We did this problem already in this literal homework. You get a triangle. Here it says we're perpendicular to the base. So here, if I cut right across the middle, straight up and down, you're going to get a rectangle. If I cut horizontally like this, it's still a rectangle. Now maybe it's a square, but I don't know that for sure, because this dimension here might be 11. Maybe this dimension here is 10.8. So maybe I'm super close to being a square, but I'm not. I'm not going to say square, because square might not be right, but rectangle for sure is right. So that's what I'm going to say. Over here, it says be perpendicular to the base and pass through the vertex. So 9 is going to be the same as 7. If I go through the vertex of a pyramid, and if I come down this front face, and if I go down that back face, and if I come across the base here, then I'm going to get a triangle, just like in a cone. So same difference. Now, 10, if I slice parallel to the base, then this again is like the prism we saw before. Every slice that's parallel to the base is going to be congruent to the base. So it's all going to be triangles. 11 wants me to be parallel to the base again. So it looks like this is a cube. So I can assume my base is a square. So now any slice I make that's parallel to that base will also be a square. Square, 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 everywhere I slice. And for 12, it says be perpendicular to the base. Now the base is this pentagon. And so slices perpendicular to the base would be like cutting across here, running down that side, cutting across the back, running down there. But all of my slices here are going to be rectangles. That's it. That's homework 12. Okay, so that's all your homeworks. Now that's not quite all your homeworks. You guys had a review sheet too, but you know what? I'm going to leave that. I'm not going to help you with that. Try to do that review sheet yourself, and you can come see me with questions on Monday. That's what Monday is for, is to go over whatever questions you guys have. So hopefully if you watched all of the videos on homework 3, 5, 7, 10, and 12, then by Monday you won't have very many questions other than questions from the review guide. So anyway, good studying. I'll see you Monday. Goodbye.